Okay, hi everyone. Welcome to this presentation on RoundMe or making rounding analysis simpler. First thing first, who am I? So my name is Jocelyn Feist. I'm the engineering director of the blockchain team at 12 Bits. If you don't know us, we are a security company where we specialize in high-end security technology. We have expertise in blockchain, but we also work on the different spectrum of the industry. We have expertise in traditional application security, cloud-native application, cryptography, machine learning, and so on. One thing that I think differs us from other companies is that we focus a lot on research, and as a result, we always try to apply program analysis to our daily job, and we have built many open source tools that you might know, such as Slither, Echidna, Caracal, and so on. But today I'm going to talk about rounding, in particular what are the type of risks that you can have with rounding, and I'm going to introduce a new open source tool which is called RoundMe. So why a talk about rounding? I believe that rounding issues are the type of issue which is frequently ignored by developers and not always considered by security researchers. There are a couple of reasons for that. The first one is that it's difficult to analyze. It's difficult to look at rounding. It's difficult to kind of try to find like one by off or things like that. Most of the time, not always, but most of the time, rounding are not going to be severe. They might lead to like a low severity issue, like you are going to have a bit of dust in the protocol, not a big deal. However, from time to time, rounding is going to be critical. Rounding is going to allow you to kind of steal the font of the protocol. So it's one of the type of issue which is usually high effort, low reward. That's why it might be not always considered. At the same time, I believe there is an overall lack of recommendation, lack of process, and lack of tooling around rounding. So that's why we're also making this talk. When I'm talking about rounding, I'm talking about precision loss. I'm assuming everyone knows about that, but we are working with number, in EVM that have a finite number of bytes for the representation. We don't have infinite precision. It's not just an EVM in any processor. It's always the case. One of the results of that, of this type of operation, is that when you're going to do a division, it's going to truncate. It's going to round down. If you look at this equation, if you remember from high school or probably even before, the left side and the right side should be equal. A multiplied by B and divided by C should be equal if you move around the order of the operation. However, if you run that on Solidity or any kind of traditional programming language, this equation is not going to be equal because you have this truncation with division. Now, this was like with direct number. Now, things become even more complex if you look at DeFi, where there is a specific representation, which is called fixed point arithmetic, which is used by a lot of protocols. The way it works is that it's to represent number which is rational, where you have a decimal, and the way it's represented is that you have the number, the dot, and what's left, and you basically multiply this number by 10 to the power of the decimal to have the representation. This is one of the representations that exists for rational number, but you can have like other one. One which is kind of famous and used for many like traditional processor is a floating point representation. You can see an example here. It's a bit more complex to manipulate, so it's not like the one that you're going to see the most in Solidity. As I mentioned, fixed point arithmetic might come with like simpler implementation, simpler with code because it might still be tricky. And if you look at the existing library, you have a lot of opportunity to use existing code base, GSMath, PRBMath, Soulmate, and so on. On a high level, when you are going to manipulate fixed point arithmetic, like if you want to do a multiplication, you are going to multiply the two numbers and divide by 10 to the power decimal. If you do a division, you're going to multiply A by the 10 to the power decimal and divide by B. This is a simplification. You have overflow risk. It's not optimized, but just to give you kind of a high-level idea. Here, sometimes through the talk, I might say 10 to the power decimal or decimal for simplification. I might just use the later one. No, because you have kind of this primitive for multiplication, which is not a direct operation, but relies on additional operation, it also lost precision. And now similar to division, you can have two directions. You can either round up or round down. So you can either have a precision that goes toward like the lowest number or the highest number. That's why when you look at some of the arithmetic library for fixed point arithmetic, you are going to find primitives to round up and down, such as in Soulmate. This is also true for any operation that you're going to build on top of this primitive, power, square root, and so on. So does this kind of loss of precision matter? Can you find actual vulnerability based on that? The answer is yes. We have seen many kind of examples, through the years of vulnerabilities that were exploiting this type of loss of precision. Now, to understand what can happen when you lose precision, let's see an example. So this formula might seem a bit complex at first, but it's a kind of simplification of the balancer type of formula for an AMM. You have a pool, you have two tokens. Token in are the tokens that you are going to send to the protocol. Token out are the tokens that you are going to receive. So you are sending some token in, you are receiving some token out. The way kind of you can interpret this formula is that the more you send token in, the more the fraction is going to be lower, and then the balance out is going to be multiplied by a number which is going to increase. Again, like this ratio, balancing plus token in is going to be less than 1. It basically represents how much you're going to increase the total supply. More you send, the lower the result. Now, if we think about kind of this fraction, and we kind of think about the case, and we push it toward the end, and we say, what happens if this wants toward 0? So if the amount of token you send is so large with respect to the current total supply that this just wants toward 0. Now you have this equation. You have token out is equal by balance 5 multiplied by 1 minus 0, which is 1. Token out is equal balance out, which is straightforward, right? Basically, you receive all the token that is within the pool. But you have to pay a lot because you have to create kind of this huge amount to run toward 0. Now you are going to ask, yes, and so, I mean, it's just a trade, you pay a lot, you receive a lot. It's kind of expected. You might think it's never going to happen. You are never going to kind of push this fraction towards the point where it wants toward 0. Now the thing is that if you think as an attacker from this type of scenario, you can think that actually maybe you can put the pool in a situation where it's unbalanced so that you can trigger this rounding toward 0, and you can do it in a way that is going to be beneficial for the attacker. So let's see an example. So we start with a pool which has 10 tokens of both. Eve has no token, she is an attacker, like the initial setup. Eve starts by doing a flash mint, and she mints a large amount of token A. Now she is going to swap all the token A that she just minted for all the token B except 1. So the pool ends up with 1 way of token B and a huge amount of token A. Now she swaps back. So she is going to send 2 token A to the pool. 2 token B to the pool to exchange for all the token A. And here, it's a rounding which is happening. So here we are in a situation where in the token B there is only 1 way. Then you send 2 to the power 2 multiplied by 10 to the power 18, and you have like this huge fraction. It runs towards 0, 1 minus 0, so token out is equal balance out. So here you are exploiting the rounding where you just send 2 tokens and you receive everything else on the other side. Then you pay back your flash mint. Let's assume there is no fee for simplification. And what's actually happening here is that you end up in a situation where you have all the token A of the pool and 80% of the token B of the pool. So basically you drain like the pool. If we go back to the equation, what was happening is that we have a rounding down on this fraction. So you can send 2 tokens to receive everything. If we were taking the kind of strategy like the opposite one and we're rounding up, what would happen is that by sending only 2 tokens, you will receive almost the same amount, but there will be 100 tokens left in the pool. Here, there is something kind of interesting, is that like the rounding might seem at first not significant because there is a difference between 10 to the power 38 and 10 to the power 20. It's a huge, like a kind of a split. But because you can inflate the number by doing flash min, flash loan, and this type of things, this kind of loss of precision become important. Okay, so what can you do here? The first recommendation that you're going to see kind of on different guidelines about rounding usually mention like the order of operation. So in some case, if you are not manipulating fixed point arithmetic, you can just kind of reorder to limit the loss of precision. For example, you should always try to multiply first and divide afterward. The reason is that if you do that, you're going to limit kind of the impact of the precision. We have a detector in Slither that is going to look for this type of issues, that it might help you to kind of detect this type of situation. However, that's not enough. If we consider formula that can be really complex, it can become really difficult to understand where you should round, if you should round up, down, and what to do. This is kind of the first formula, but I just added a couple of parameters. Don't try to kind of think too much about what they mean. It's just, for example, I wanted to make a formula a bit more complex. Here, we still have token out, that is going to be the result of the formula. So we want overall to random. We want the result of this equation to be as minimal as possible, to not be profitable for the user, but to be profitable for the protocol. We have two components, it's a multiplication, left multiplied by right. So because we want to round down, everything should round down. Multiplication should be down, the left side should end up being down, right side should end up being down. Now things are going to become a bit complex. Here we have a number which is to the power of a fraction. We want this overall number, so A on the power on C on D, to round down. If you think about it quickly, you will go toward the direction of saying, okay, everything just needs to round down because, like if you multiply something again by a power and it's like you want the overall result to round down, everything needs to round down. However, if A is a number between 0 and 1, it's actually the opposite. If you think about it, 2 to the power 3 is going to be below 2 to the power 4. However, if you have something like 0.5 to the power 2 is not going to be below 0.5 to the power 3, because if you multiply a number between 0 and 1 by itself, more you multiply it by itself, the lower the result will be. So this is an example where you can see why sometimes it's complex to think about rounding, because the rounding direction is going to depend on the values context. The good news is that usually in this type of protocol, when you have a value which can be between 0 and 1, you can identify which one they are going to be. Might be a system parameter, might be something that represents like a percentage. If we look at the right side, we also need to round down again. But here we have a formula on the kind of the format 1 minus something. If we want the overall 1 minus something to round down, we actually need the something, the x, to round up. We have 1, and more you kind of subtract this number, it's going to go towards the second direction, the opposite direction that you want. And you can continue like that. You have like, a power operation, and you can continue to apply this type of rules. So basically, to analyze this type of situation, what you need to know is that you need to go step by step through every operation and apply the rounding toward being beneficial for the protocol. You should really avoid any situation where the rounding is going to be beneficial to the user. You can start from the outer component of the expression and then go step by step into the inner components. There are a couple of tools that are going to help us to kind of identify this type of issue. The first one is a fuzzer. Fuzzers are really good to find a rounding issue. You can try to see if you can make a profit out of the swap and things like that. I'm going to introduce in a couple of slides a new tool, RoundMe, that is also going to help you to identify which direction you should take. Now, if you are a developer, what can you do to make this simpler and to kind of avoid having rounding issue? The first things to do is to create primitive for every rounding direction. You should have a primitive to round up and primitive to round down and make it explicit. It's really important that you kind of understand for every direction which one should be taken. Something to consider also, and you have to play a bit with your formula, is how you can express this in a way that is going to reduce the loss of precision. The first thing I mentioned before, multiply before divide. This is a simple rule that you can follow, but it's not necessarily enough. You might also be able to kind of refactor the formula in a way that is going to reduce the number of operations that leads to precision. All the examples I've given so far are on unsigned fixed point arithmetic. If you are working with signed fixed point arithmetic, things become even more complex because the rounding direction might be depending on the sign of the expression. So if you are manipulating this type of expression, here you should try to kind of avoid having expression that can be both sides. And to do that, you might be able to rewrite your formula in a way that the expression that can be both sides comes at the end. So try to maybe factor some components or things like that so that you can always reason within the same side. The last thing, and this one is really, really important, and I think a lot of people kind of forget about it, you need to document and you need to test every non-loss of precision. If you know like that a specific rounding direction has to be applied, document it, just one line before your operation, explain why you are doing the rounding. And have a unit test to demonstrate that this is what you're actually intended to do. Having this kind of inline documentation and testing is going to help you to make sure you really analyze every direction, and it's going also to help people that are reviewing your code to understand what you are doing and to understand that the direction you are doing follows the principle of being beneficial for the protocol and not for the user. Okay, as I mentioned, we have created a new tool to help you to analyze this type of rounding issue. It's called RoundMe. So RoundMe is a human-assisted rounding analyzer. The way it works is that the user is going to provide the formula as a text, and RoundMe is going to automatize this step-by-step process that we just went through with the example. It's open source. It's in Rust. I know a lot of people love Rust, so some of our tools are now also in Rust. It's on an early stage. We only have a couple of rounding rules. By rounding rules, I mean this kind of situation where, for example, you have 1 minus x, and when you have 1 minus x, you need to apply kind of specific strategy. It only works with unsigned fixed-point arithmetic for now. We are going to work toward integrating signed fixed-point arithmetic. Hopefully, most of the protocol don't use yet this type of complex formula. To give you an example of how to use it, you just run RoundMe config, you write the formula that you want to analyze, you provide the direction that you want to do, up and down, and then the tool is going to ask you a couple of questions based on the rule. For example, the example where I mentioned where you need to provide the information if the number is between 0 and 1, the tool is going to ask you. It's going to generate a config file, which looks like this, exactly what you just provided. Here, again, we work with text. We don't work directly with the source code to make it more easy to manipulate and make it kind of easier to write different formula. As a result of the analysis, RoundMe is going to generate a report in latex.pdf, which is going to look like this. So here, for every multiplication and division, you have an arrow, which one down or which one up, based on the direction that you should be taking. So typically, like, if you are building a protocol, you should always try to write the formula in a way that you can express them and in a way you have this information. Because now, when you go over like the implementation itself, you can compare that the implementation follows this kind of specification. Okay, so to conclude, I think it's important to really pay attention to the rounding. As a developer, you should really make all the rounding explicit. Make sure you test them, make sure you document them. Hopefully, RoundMe is going to help you to understand which direction you should take. As a security researcher and as a developer, you should also use a fuzzer to stress test your rounding and make sure you are not losing precision the way which is intended. If you are interested in fuzzing, we are actually giving a workshop today at 6 p.m. in the sponsor zone on Echidna. More generally, we also created a new kind of offering, which is invariant as a services. Over the past years, we have helped a lot of our clients to develop invariant and to integrate further in their development pipeline. As a result of that, we kind of leveraging all the experience that we have gained over the year to create the services where we help our customer develop invariant. If you're interested, come talk to us at the booth or later with me directly. Thank you for your attention.